All right, thanks so much. And today, my talk is going to be a recent update on molecular dynamics simulation of hypervelocity impact. And we're hoping to share some remarks on the influence of those clustering on velocity distribution functions as well. And I want to start with a picture taken by Cassini missions. And this is a picture showing the plumes on Enceladus. And there's so many kinds of molecules and ice grains on those in those plumes, and some of them actually contains astrobiology information. So this actually brings more interest in investigation of those plumes. And Europa Clipper mission is going to is planning to visit the plume regions of Europa, and the surface dust analyzer is the instrument that made specifically for the measurement of ice grains in these plumes. One of the most important parameters that the surface dust analyzer is going to measure is the velocity of those ice grains. So previously, missions such as VAL2 used an aerogel to collect those any materials or dust from the comet. Alternatively, people have been using a polarizable polymers to measure the impact-induced charge change and to infer the velocity. But the challenge for measuring those icy grain is water ice is actually very volatile, and upon hypervelocity impacts, it can easily be evaporated or fragmented. So this makes it very challenging for the measurement of velocity. And in order to understand the hypervelocity impact of ice, there has been some lab experiment. For instance, the impact team has this dust accelerator to create a hypervelocity impact on those cryo icy surface. And people have been using these pulsed IR lasers to shoot on a water beam, and they managed to create some mass spectrometer detected from cosmic dust analyzers. So this is very promising. In this study, we're hoping to use the reactive molecular dynamics simulation to see what's happening during this hypervelocity impact. And here on the left panel, we are showing the setup. This is a nano-sized ice grain, contains about 7,400 water molecules. And we're testing the velocity from 1 kilometer per second to 24 kilometers per second, hoping to cover the whole range for the average impact velocity of those ice grains. And we're also showing a snapshot, so you can see the hydrogen bonds between those two water molecules. And we also have trimers, which are 3 molecules attached to each other. And we're also having a very large cluster showing in figure C. What I really want to show you is it's the one on the bottom. So this is we call pseudo max spectrometer. We're basically doing the same with those lab experiments like max spectrometer. But instead of counting the mass of those clusters, we're counting the number of items because we can directly find them from the molecular dynamics simulation. And you can see those 3 N beams are actually shows very clear signals, and they're representing like single water molecules, water 2, water 3, etc. And you're also seeing some 3N+1, which are like atomic hydrogen attached to a water cluster, and 3N-1 is basically a water cluster losing a hydrogen. So these are actually evidence of fragmentation or ionization, if you call it. And the size distribution of those water cluster actually follows a power law distribution as indicated by previous experiment. And we also derive the power index, and we plot it against the vertical component of the velocity. So up to about 3.6 kilometers per second, we see a very consistent power index value compared to the previous experiment. But beyond this point, we're seeing a very clear declining trend, and also the variation of those power index become larger and larger. So this actually, this has become interesting because this 3.6 kilometer per second is actually corresponding to the energy needed to dissociate a single water molecules. So we realized that the high pressure and high density region created by the intercalation between those reflected water molecules and impinging water molecules actually have a different process starting from the 3.6 kilometers per second. So we call the velocity range before 3.6 intermolecular fragmentation, which the impact only breaks up the hydrogen bonds between water molecules. And beyond 3.6, we call this interatomic fragmentation because the impact energy is actually high enough to break up the covalent bond between the hydrogen atoms and the oxygen atom in a single water molecule. So in this interatomic fragmentation, because we have a lot of free hydrogen items and oxygen items, so it's highly likely that some chemical reactions can happen. And indeed, we actually found the generation of molecular hydrogen and molecular oxygen. So we're plotting this yield of H2 and O2, which are the number of those new molecules over the 7,400, which are the number of water molecules in the setup. And you can see those two peak lines indicated by the dashed vertical lines. They are actually the energy that is high enough to dissociate this H2 molecules and O2 molecules. So it's high enough to break up the HH bond and also the OO bond in here. So this got interesting because we think in this interatomic fragmentation range, the power index become very large, the variation of the power index become very, very large. So indicating that power index might not actually be the best way for the velocity probing. But we actually have this relative yield of H2 and O2 have a very good linear fitting with R square around like 0.97. So we think because we can directly obtain the abundance of molecular hydrogen and molecular oxygen from the mass spectrometer. So once we have those data, we can find the relative yield, and then we can use this linear curve for the velocity probing. And furthermore, with the benefit of molecular dynamic simulation, which explicitly simulate the dynamics, we are able to put some remarks on how the chemical reaction actually affects the velocity distribution of those ejectas. And here I'm comparing the velocity distribution function of a single water molecules, which in blue, and also a dimer, which are two water molecules attached by a hydrogen bond. They are in orange. So we're using the Maxwellian distribution to fit the data we have, and we roughly found a two-fold relationship of the equivalent temperature here. And in this way, we constructed a mixed Maxwellian distribution, which combines the power law distribution for the weight of those different clusters distribution function. And for the cluster distribution function, we basically substitute the actual mass of this cluster instead of using the single water mass for the VDF. And here you can definitely see a difference between those two. We're also like plotting the escape velocity for Europa, Moon, and Mercury for those dashed lines. And by comparing the portion of this velocity distribution function against the escape velocity, and we can basically see how many molecules are still surface bounded after the impact vaporization, and how many molecules are actually lost to space. So this actually means there's a huge difference between, if you consider impact vaporization on an icy surface compared to, water that are bounded with silica surface. So to put a conclusion here, we discovered a two-stage fragmentation, namely intermolecular fragmentation and interatomic fragmentation. We also found the psi distribution follows a power law distribution for the interatomic fermentation stage. And we also found chemical reactions are very, very active, and it can generate some new products during this interatomic fermentation range. And also this chemical reaction information can be used for velocity probing, because the power index is no longer in good shape. And also the overall velocity distribution function for icy surface is definitely different from that of single water molecules bonded with silica surface. And we once again emphasized, we're using this reactive molecular dynamic simulation, which combines chemical reactions and dynamics together. And this can actually reveal a lot of information about all of those planetary processes on the Moon, Europa, and also Mercury surface. All right, with that, I will take any questions you may have. Thank you.